G'day chemistry students. In this video, we're looking at dot points 5.4.4 and 5. There's two more concepts to cover for the quantitative aspect of this module. It's the common ion effect and something called the assumption. It's a term that I've sort of coined because there's not really a good name for it, certainly not a common name that's used. But this assumption is something that we can use to simplify calculations when trying to determine the concentrations of unknown substances in equilibrium. But anyway, let's get into it. First off, I want to be looking at this common ion effect, and I want you to sort of think about these two statements that I've got here. First one is, if I add sodium chloride to hydrochloric acid, what that's going to end up doing is influencing the solubility of sodium chloride. The solubility of sodium chloride in water will not be the same as the solubility of hydrochloric acid. But conversely to that, if I have sodium chloride and add it to a lithium sulfate solution, I'm not going to have that exact same effect be observed. Essentially, the lithium sulfate won't have as much of an impact, if any impact at all, on the solubility of the sodium chloride. And my question to you is, why is there a difference? Why would the solubility here be so impacted? Now, the short answer is that the scenario that I gave you had common ions. The chlorines or the chloride ions are present in both of those substances that will be mixed into the solution. And that will influence the amount of soluble ions that can be present in solution. So we know that Ksp is equal to the product of the anion and cation concentration. And if I add sodium chloride to hydrochloric acid, that's going to change the solubility of sodium chloride. The general concept is that the Ksp will be constant whether or not the sodium chloride was in hydrochloric acid or in water. What's different though is that in the hydrochloric acid, there will be more chlorine ions present. The concentration of chlorine in solution will increase. Now, what that means is that the sodium concentration will need to be lower so that we ensure that the Ksp stays constant. As a result, if the concentration of sodium is going to be lower in a hydrochloric acid solution, overall, there's going to be less sodium chloride that can actually dissolve, which means that its solubility will be lower than normal. Slightly different way of justifying that, using a little bit of math to sort of build out that justification that I gave. I said before that if there was going to be lots more chlorine than normal, that the sodium concentration will be lower than usual, and that will be to ensure that Ksp remains constant. So with some quick little math, I can sort of prove that idea. To do so, I'm going to say that the Ksp for sodium chloride is 4. That's just a made up theoretical value, but it's going to make things a little bit easy to see when the math sort of gets applied. So if I have a pure solution of sodium chloride, just sodium chloride into distilled water, the solubility product would be in a 1-to-1 ratio, meaning that 2 times 2 molar would be equal to 4 our Ksp. But if we were to have a solution of sodium chloride where there was already chlorine, let's say that when we put everything together, the ending concentration of the chlorine is going to be 4. That's going to mean the concentration of the sodium needs to be 1 so that the solubility product at the end still remains 4. So the concentration of sodium up here was 2, concentration of sodium here was 1. That means that the concentration of the sodium, as I said up here, will be lower than normal. As a result, because not all of the sodium has dissolved, or certainly not the maximum amount of sodium has dissolved, the concentration of sodium chloride will be lower than normal. This concept is probably a lot easier to see when you actually go through a calculation, but hopefully that justification may make sense either now or afterwards when we do that practice question. Last thing to include is this idea of the assumption. And this assumption only works when we're looking at an equilibrium system where the K value is really small. So for Ksp calculations, that's when we're looking at insoluble or partially soluble substances. There are other applications when we are looking at small K value systems, but for now we're just looking at it in terms of solubility. When we have an equilibrium system like this, there are times where it's very convenient to assume that where there would be a concentration change that we could probably show in an ice table, that change is going to be so small that the initial and equilibrium concentrations are pretty much just the same. When you employ this technique into a problem solving question or a calculation. The technique means that you don't need to use some complicated math to actually be able to find or solve for the unknown concentration. A lot of the time, that would mean that you would need to use a quadratic formula, which isn't meant to be a required part of this course. So, for example, if I had silver chloride solid and put it in a solution of 1 molar hydrochloric acid, the chlorine concentration at equilibrium will be 1 molar at the beginning and 1 molar after we put the silver chloride into the solution, at least accurate to two significant figures. Technically, there will be some more chlorine that actually dissolves into the solution from this silver chloride, but the amount that dissolves is not much at all. If you look at your data sheet, silver chloride has a very, very, very low solubility. Its KSP is 1.77 times 10 to the negative 10, quite a low value. So when you put silver chloride in, there will be a tiny amount of chlorine which dissolves, but not enough to change the overall concentration of chlorine that is present in the solution. The amount of increase that we get will be negligible. Whatever is added on will still be rounded to 1.0 molar to two significant figures. Now, this concept again is a lot more easier to understand once you've seen it in practice and once you're using it in your own practice questions. So we'll jump into the practice calculation for this video and then do some additional practice when in class. But let's get into our practice question today. Okay, so in this question, we're being asked to quantitatively compare the solubility of magnesium carbonate in a 0.50 molar sodium carbonate solution with its solubility in a 0.375 molar sodium carbonate solution. So the first thing that I'm going to do in this question is just pick apart some of the key pieces of information that we have. So we know that we're looking at the solubility of magnesium carbonate, and that's based on the KSP value that's been given. However, we've been given some information about two different solutions that it's going to be sitting in. So for both of these solutions, it's not just going to be magnesium carbonate in water, but magnesium carbonate being put into sodium carbonate solutions of different concentrations. So as usual, best thing to do to start off with is write down the equilibrium equation. So we have magnesium carbonate, and we know that that is solid, and that it is in equilibrium with its ionic components. So magnesium ions and carbonate ions. From there, we can also write a KSP equation. So that's going to be the concentration of magnesium present in the solution multiplied by the concentration of carbonate ions present in solution. So the first thing that I'm going to do is just split my page in half because we're going to be doing two solutions for this one. The first is on the left, we're going to be doing a calculation for magnesium carbonate in a 0.375 molar solution of sodium carbonate, as well as magnesium carbonate in a 0.550 molar solution of sodium carbonate. Now, what I want to do first for both of these is draw up an ice table for all of our ionic components. And again, that's for our magnesium carbonate, our magnesium ions, and our carbonate ions. Now, for both of these tables, we don't really need to worry too much about the magnesium carbonate solid, as it's not going to have a concentration at any point. What we do care about are our products, our ions, and what they start and end as. So magnesium in both of these, there's going to be no concentration for magnesium ions initially, but there is going to be a concentration for the carbonate, and that's going to be coming from our sodium carbonate solution. So depending on what the concentrations are, that's going to dictate to us what the concentration of carbonate ions are going to be in solution. So they're just going to match the molarity of the sodium carbonate solution, essentially. And that's because the carbonate ion is in exactly the same ratio as the sodium carbonate units. Should put a 2 here just to fix that up as well. Now, once we get to this point, we know that there's going to be a change in concentration. Some of the magnesium carbonate is going to dissolve. We could say that there would be an increase in X concentration for both of these, and that's going to be based on the amount of magnesium which actually dissolves as well. Now, that's going to be the same for the carbonate ions. It's also going to be a plus X. So that means that we're going to end up with a concentration of X at the bottom of both of these. And the concentration of the carbonate is going to be the original concentration plus the additional. However, when we're looking at this statement here, this is where we can start to employ the assumption. So because X is going to be a lot less than the carbonate concentration that we have at the beginning, and this is because of this value up the top here, which is a really, really, really small KSP value, meaning that the magnesium carbonate is going to yield a very low concentration to begin with. So because there's going to be a really big difference between the amount of extra carbonate that's been added and the concentration that's already there, we can say that the concentration of the carbonate ions at equilibrium is going to effectively be 0.375. We can use exactly the same logic over here as well. I'll quickly replicate that. So because that's the case, we can use that kind of information to make our life a little bit easier when going through with our equilibrium calculation. So that's only going to mean that we have one X term in both of our problems that we've got to solve. So we know that the KSP is going to be equal to the concentration of magnesium, that's this one here, which is X, times the concentration of our carbonate, which we know we don't have to include X for anymore. So that's 0.375 for solution number 1. And then for section number 2 that's over here, very similar equation is going to be written up as well, just using a different concentration of carbonate. So rearranging those equations, we should be able to solve for X. That's going to be our KSP, which is 6.82 times 10 to the neg 12. That's just come from our data at the top. We're dividing that by our concentration of carbonate, 0.375. Very similar over the other side. The only difference is going to be the concentration that we're putting in on the bottom, 6.82 times 10 to the neg 12 over 0.550. So let's get that into our calculators and get our final answers. So for our first problem, the answer is going to be 1.82 times 10 to the neg 11. And for the other one, 1.24 times 10 to the neg 11. So these X values represent the concentration of magnesium ions that will end up being in solution. Effectively, that means that that is going to be our concentration of magnesium carbonate. Now, I don't have to multiply this up or divide anything at all because the ratio of magnesium ions to magnesium carbonate units is 1:1. The similar thing over here, I've got my magnesium ion concentration. This is effectively the same as the concentration of the whole magnesium carbonate unit. And we can use this to make a comparison. So these are our concentrations in moles per liter. Now, what we should see is that the concentration of magnesium carbonate in a 0.375 molar solution is greater than the concentration of magnesium carbonate in a 0.550 molar solution. And I should probably just note of carbonate ions. So if this is the case, then the magnesium carbonate has a higher solubility in a 0.375 molar solution of sodium carbonate compared to a 0.550 molar solution of sodium carbonate. And there we go. We have been able to use a quantitative measurement, compare our solubilities here to determine where magnesium carbonate is going to be most soluble based on its KSP. Thank you very much, everyone. This video is our conclusion for Module 5. Well done. Congratulations. You guys have worked really, really well over this first term, which has been awesome to see. I look forward to seeing you in the next module for Module 6, which is all about equilibrium and acids and bases in particular. But until then, have a good one.